Hello everybody, this is Vipul Purohit and I welcome you back to my YouTube channel. My dear friends, right now in this particular session we are into the discussion of two important concepts associated with chemical kinetics, and they are Arrhenius equation and collision theory. So we begin with the first concept, and that is Arrhenius equation. Now basically Arrhenius equation is related to the effect of temperature on the rate of a reaction. Yes, my dear friends, the rate of the reaction generally increases with increase in temperature. And generally it is being found that for every 10 degrees rise in temperature, the rate of the reaction doubles. Now this is going to be postulated in terms of an expression, and that is called as an Arrhenius equation. So according to Arrhenius theory, as the temperature increases, the reactant molecules acquire thermal energy, and as a result of which their collision frequency increases. This results in an increase in the number of molecules reaching the transition state and thereby forming an activated complex. Thermal energy, my dear friends, is required to overcome the energy barrier, and the rate at which the collision takes place will also increase, and as a result of which the number of molecules which is going to reach at the top of the energy barrier, that is a transition state, or we call it as the activated complex, will increase. Now the fraction of the molecules F which gets converted into the transition state, that is the reactant molecules whose energy level is less getting converted into a transition state where the energy level is high, is given as F is equal to e raised to minus of E upon RT, where capital E, small e, of course you know it's exponential. The capital E stands for energy of activation, capital T stands for absolute temperature, and capital R is gas constant. Now as a result of which the rate constant, when we talk about, that is K is a rate constant, is directly proportional to F, that is the fraction of the molecules. More the number of molecules reaching the transition state, and you know guys very well, molecules reaching the transition state very fast gets converted into the products, and therefore we say greater the number of molecules reaching the transition state, greater is the possibility of those molecules getting converted into the final products, and hence the rate of the reaction increases and the rate constant also increases, and hence we say that K is directly proportional to F. Therefore we say that K is directly proportional to F. If I want to remove the proportionality sign, I introduce a constant, that is A. So we have K is equal to A into F. Now what does A stands for? It's Arrhenius constant. Now if we are going to substitute the value of F which we had over here in this particular equation, we have K is equal to A into E raised to minus of E upon RT. This is equation 1. Now if I want to write down the equation 1 in the logarithmic form, then I can write it down as ln K, that is log exponential or natural log, is equal to ln A minus of E upon RT. Right? Now when I consider rate constants K1 and K2 at two different temperatures T1 and T2 respectively, then this same equation 2 can be written as follows, and that is ln K1 is equal to ln A minus of E upon RT1. Similarly ln K2 is equal to ln A minus of E upon RT2. Okay, now here my dear friends, please remember the condition is T2 is greater than T1. That means T2 is at a higher temperature as compared to that of T1. Now if we are going to subtract these two expressions, that is 4 minus of 3. So what we have is ln k2 minus ln k1. So if we apply the logarithmic rules, we will say it is ln k2 upon k1 is equal to, now ln a minus of ln a gets cancelled. So we have an e upon r, I'm going to take it as constant. Okay, that is common, e upon r. So in the bracket, I will have 1 upon t1 minus of 1 upon t2. Now how it is so? It's only because that we have done 4 minus of 3. So this is minus over here. Minus is associated with 1 upon t2. So you can see this minus is associated with 1 upon t2. And now minus is already over here. And plus we have a minus over here. So minus and minus becomes plus. So t1 is associated with positive. So see here, t1 is associated with positive. And therefore we are now writing as 1 upon t1 minus 1 upon t2. Now natural log I converted into log to the base 10. So I have 2.303 log k2 upon k1 is equal to e upon r 1 upon t1 minus 1 upon t2. And hence, my dear friends, the energy of activation can be determined with the measurements of k1 and k2 at the two different temperatures T1 and T2, where T2 is greater than T1. And this is, my dear friends, the Arrhenius equation, which resembles the effect of temperature on the rate of reaction. So I hope you have understood up to this very well. Now, my dear friends, we move on to the second part of this particular session, and that is collision theory, under which we are going to learn only 2 points, okay, and that is postulates and its drawbacks. So let's start with the postulates. Number 1, the molecules are treated as rigid spheres. Okay, that means they neither be expanded nor being contracted. And we are going to consider only their translational motion. That means we are going to make sure that the molecules neither vibrate nor rotate. Point number 2, reactant molecules must collide for a reaction to take place. This is a very essential condition, my dear friends. Okay, collision must take place, and that's the reason the name of this theory is collision theory. So the collisions must take place amongst the reactant molecules, and then the reaction takes place. Now what happens during these collisions? Only an exchange of energy takes place, that's it. But there is no net gain or loss of energy of the molecules. Alright, that means the energy of the molecules remains constant. The total energy of the molecules remains constant. And such collisions are called as elastic collisions. Okay, they are called as elastic collisions. Next, number of collisions between the molecules which are treated as rigid spheres can be calculated by means of kinetic theory of gases. Okay, kinetic theory of gases proposes the calculation of the number of collisions which are taking place between the molecules, because as I said that the most essential condition for the reaction to take place is collisions. So obviously the rate of the reaction is directly proportional to the number of collisions. Alright. Now the next point is, during collisions some molecules may gain and others may lose energy. Okay, so that means only there is transfer of energy, but the total energy remains constant. Next point is, only those molecules which possess energy above a certain minimum will react upon collision. And such collisions are called as effective collisions, for which the molecules must be suitably oriented. Okay, it means what? That all collisions are not effective collisions. All collisions does not relate the reactant molecules being converted into products. Alright, so for effective collisions, only those molecules which have a certain minimum amount of energy, only those can be converted into the product molecules, and those are responsible for the reaction to take place. Alright, so such collisions are called as effective collisions, and hence we can say that the rate of reaction is directly proportional to effective collisions. Okay, we are now slightly more specific. Okay, initially we said it's directly proportional to the collisions, but now we try to be more specific by saying that they are directly proportional to effective collisions. Next, when molecules take part in effective collisions, then the rearrangement of bonds takes place in the reactant molecules, and thereby it results in the formation of product molecules. All right, and the last point is the rate of the reaction is directly proportional to the number of collisions taking place per unit volume and per unit time. All right, my dear friends. So these are the important postulates of collision theory. All right. Now, as I said earlier, in this particular section, we are only going to consider two aspects of collision theory. One, postulates, and the other is drawbacks. So we move towards the drawbacks. The important drawbacks only we are going to consider, and that is the first one is this theory is applicable only to simple gas phase reactions and not to complex reactions. Okay, and whenever we have complex reactions, this theory not to be taken into consideration. Next, this theory does not take into account the steric factor. Okay, that means when we talk about overcrowding, the distances between the reactant molecules. Okay, so this theory does not take into account the steric factor which are associated with the orientation of the reactant molecules. Point number 3, this theory considers only the translational energy of the reactant molecules, and it completely ignores the rotational and the vibrational energies. If you remember this, I told you in postulate number 1, okay, there are possibilities that the molecule may not be completely rigid, and if they are not completely rigid, then obviously there might be to a certain extent rotational and vibrational energies also. But this theory considers only translational energy. Next point is, this theory does not explain the processes of bond breaking and bond formation. It just talks simple about one word, and that is rearrangement. That's it. But which bond is broken, which bond is formed, and the mechanism behind that, okay, during a chemical reaction is not explained by this particular theory. All right, my dear friends. So this is about the drawbacks of collision theory, and this is what we have to discuss in this particular session. So I hope you have understood both the aspects, that is the Arrhenius equation as well as the collision theory. So thank you so very much for joining me today. Thank you. Bye-bye.